Good day, everybody. We're going to continue with the third part of this chapter, and we're at 11.3.3, which is operations on linked lists. And today we're only going to look at one operation, and that's basically how to search a linked list, because there's quite some coding involved, and so we will look at this in quite some detail. And then on the final lecture for Thursday, we will look at some of the other operations. Alright, so we can do the same operations as that we have done on arrays. So for linked lists is the same kind of things that we can do. We looked at arrays and we saw that for arrays we could also delete and insert elements and so on, but there was significantly more work to do in an array, because by nature an array, as you know, is stored contiguously in memory. So all of its elements are literally next to each other in memory, and so if you have to delete one from the middle, it means you'll have to delete that entire one, delete that one and move all the others, all the remaining ones, one position up, so that it remains contiguous in memory. And as I say, that's not usually something you do in arrays. With an array, it's usually a fixed thing, but this is where you'll start seeing now the real power of linked lists coming in. Not even only in really in this lecture, but in the following lecture, where we will look at how we can insert and delete nodes from a linked list and so on, and how easy that actually is compared to the amount of work you had to do, not just by coding, but also in terms of operations cycles, really, that the computer has to process. Alright, so searching a linked list. So now we know that since nodes in a linked list have no names, we use pointers to point at those. And we're going to use two specific pointers for this case to keep track where we are currently in this linked list. So we're going to use a pre pointer. It's called pre, P-R-E. That's naturally going to point to the previous node. And we're going to use the cur pointer, short for current, which is actually then pointing to the current element or the current node of the linked list. So that's the two pointers we're going to use constantly, and those two pointers need to be updated as we move along to this linked list. And you'll see how that's going to happen. Now at the beginning of this the search, the pre-pointer is null, because imagine if you are pointing at the first element of the list, the current pointer is going to point to that, and there's going to be no node before that, and that's for that reason the pre-pointer is going to be null. The search algorithm moves the two pointers simultaneously to each element one by one, and eventually toward the end of the list. So with this approach, when we move it on one, then basically the idea is just to point or to move on to the next node. We don't jump to other nodes like skipping a few or whatever. It's always just actually moving the pointer one on. Now figure 11.13, which we will actually view at the end of this lecture, shows the movement of these two pointers. Sorry, we will do that just now. At the end of the lecture you will see the full algorithm. That's what I actually meant. But figure 11.13 shows the movement of these two pointers through the list in an extreme case scenario. So we're going to have several case scenarios. Okay, but in this particular one, the scenario is when the target value is larger than any value in the list. For example, we're going to search, say, for the value 215 in the linked list, and it will not be found in the list, which means we would have went through the entire list and not find it. So let's look at the scenario. Okay, so here you can see what we have is a linked list. So this is the linked list over here, and The linked list is basically starting over here with the head pointer. So you already know what the head pointer is. It's that pointer that points to the first element of the linked list. Now, say for example, I mean, everywhere you will see it's just pointer shown here, but what happens reality, as we showed in the previous lectures, maybe this particular node starts, say for example, at address number or at byte number 334, just as an arbitrary number that I'm choosing here now. And if this node basically will take up 2 bytes, then it actually means that this particular position or starting point is actually byte 335. In other words, the actual data as well as the pointer together makes basically the node. It makes up the node. So we assume in these examples that nodes take up 2 bytes in this case. So basically what it means is that what is written inside this particular box here is just the address that it points to. So in other words, technically what you'll find inside there is the value 334, or otherwise called the address 334. So that basically means this head pointer points to address 334, which basically is the start of the node over there. And so every other pointer, like this one for example, if this maybe was at address starting at address 641, then technically what you will find stored inside here is basically 641. All right, so it's the address of that, and so it goes on. All right, so over there pointing there, and this last one pointing there. And note that the very last pointer, there's no pointer. In other words, this is typically called the null pointer in ULL. So nothing is stored actually in there. It's just the null character. Okay, so now that you again have just that little bit of revision, so you can see the linked list over there, and then when we start off by searching, the current pointer here points to the first element. So just in terms of this, in other words, the current pointer would also hold the value 334, because the current pointer is actually also pointing to the beginning of the list at the moment where my list pointer or the head pointer is pointing. And that's for that reason the values inside of the list pointer and the current pointer are the same. They are pointing to the same address, in other words to the same node. Note that the pre-pointer, as you can currently see here, does not have any value. In fact, the value technically inside there is the null pointer. Okay, so this is at the beginning. Then what needs to happen is after one move, basically what we need to do, if I just show again here from the start, what will have to happen with the next move is that my current pointer now needs to point over there, and my pre-pointer or previous pointer needs to point over there. So basically what will have to happen is that my current pointer, this one over here, by pointing over there, it will need this address. So basically the current pointer now gets the address of the next node, so that basically now it also points in this example to memory position 641 for argument's sake, and the pre-pointer simply will get the value of the current pointer. Okay, but now it's important to realize that the order is important here. The first thing that will happen for this move to take place is first that we assign the current pointer to the pre-pointer. In other words, currently the current pointer has the value 334. So therefore, by assigning that, we now give the value 334, in other words the address 334, to the pre-pointer. So now the pre-pointer would also be pointing to what the current pointer was pointing at this stage, and only then the current pointer gets the value of what this thing is pointing to its pointer. In other words, 641, as I've explained over there. A little bit later I'll show you in an animation, and then it will even become more clear. Okay, so after 4 moves, basically we end up by going through right to the end, that as soon as the current pointer becomes null, it means we're at the end of the list, because the current pointer does not point to anything, which means we have gone through all the elements, and the pre-pointer would be pointing to the last element of the list. Okay. Note though, and this is very, very, very important, we make an assumption here that the data is already in ascending order. So you can see in the order, it's from low to high, first 102, then 132, then 178, then 201. So it's already in a sorted order. We don't do sorting of the lists here in this course, but obviously sorting can be done, but we're not going to do it in this course. Right, so let's look at the values pre and cur, the previous and current pointers, in different cases. So we will quickly examine a few cases. The first case we're going to examine is a case where we will have to search for a value that first of all does not exist in this list. And as you can see, the target value we're searching for in this case is 98. So in other words, we would assume that we would be searching for 98, but if we get to the current and the first pointer, basically, which is this one, and realize that it's 102, we already know that we couldn't find this. Right at the beginning of the list, we couldn't even find it. So it's not there. Okay. In the next case, we're going to find the target somewhere in the list. So in this case, we do find it. Now, just look that we are going to use a variable here called flag. So it's just flag is just the name of a variable. It's like a flag goes up if something is found. So a flag is only risen, so to speak, when the value is found. So that's why in this case the flag remained false, because we couldn't find the variable. But in the second case, we were searching for 132, and we actually did find 132 in this list, and for that reason the flag was set to true to indicate that we did find it. Okay? But there's also another case here, a third case, where we would search for a variable. It might have been found somewhere in the list. It's not a case that we didn't find it even at the beginning of the list or even at the end of the list, but it was supposed to be somewhere in the middle of the list, but we realized also that we didn't find it, so the flag remains false. So in this example where we try to find 150, it would have been between 132 and 178, but it wasn't there. And for that reason, flag remains false. And in the last case, we're going to search for it and actually find that we had to traverse through the entire list and didn't even find it, meaning that the target, like 305 in this case that we were searching for, is actually at the end. So all 4 of these cases we will now do in more detail for the remainder of this lecture. Let's start with the first case. So this was the case where we had to go and find the target, and we would found that the target is actually less than the very first element, which means it's a case where we couldn't find it, even when we looked only at the first element. So here we actually find an algorithm on how to do that. Just a note on this algorithm. This algorithm have been modified and made more simplistic. Algorithm 11.3 at the end of this lecture will be more complete, and then you'll see the complete full picture. But for now, it's actually been simplified just to make it easier for you to follow here. So what we're going to do here is to actually try and figure out while with this loop here, while current is not equal to null. All right, so that means we still have elements to traverse. So the moment that current actually gets to this point over here, which means it will, well, it will still point to that element, but then when we advance and it actually points to null and the pre-pointer points to this, it's in this scenario when we know we must stop. Okay, so while our current pointer is not equal to null, we may continue to search here. So obviously the current pointer in the first case here points to the first element and it's not null. Okay, so now we check and we follow something here again by indicating first what are we looking at here. So the current pointer, so the asterisk here basically says it refers to the current pointer. So it refers to basically that thing. All right. So that thing that it points to, what does it point to? What does the current pointer point to? Points to? It points to this one at the moment. All right. Technically, it points to the beginning address, but basically it points to this node. Okay. So if it points to that node, dot data, then we actually mean we are talking about the data part. That. All right. So that's how to refer to the data part. We've done that in the previous lecture. So the current pointer, and remember the brackets here around star car means that we are talking about the pointer of current. In other words, what it points to this thing over here, and dot data means specifically to the data element, which is 102. So is 102 equal to the target? The target is 98. No, it's not. All right. So if that happens, we have to try and search further. Now, technically, we could make this algorithm better by stopping to search here at the moment, but to make it just simple, to see how it continues searching through the entire list, basically, if this was the case, if it was equal to the target, it would have set the flag to true. But the flag remains false at this case, and then it would return. Return means end this entire loop and continue with what's after this loop. Okay, and this syntax we're using here is mainly C and C++ syntax. Right, so this is not the case clearly at the moment. So target is 98 and current pointer dot data is 102. So it doesn't match. So at the end of the if, what do we do now? We basically say current gets the value of current is assigned to pre. So whatever current points to now is assigned to pre, which means pre would also at this very stage point to current. And then we advance the current pointer. Now this is a strange way of advancing a pointer because we say car plus plus. Now just a little bit for those of you that might not know this, if I have a variable like I, and let's say in memory there is the variable I and it has the value 5, we assume that, and we say I equals I plus 1. Then basically what happens is that the computer takes I plus 1. What is I at the moment? It's 5. All right. 5 plus 1 would give us 6, so the result of this would be 6, and that will be assigned or stored to I. In other words, it will just simply go and overwrite what is in there now. In other words, I will now have the value of 6. But I equals I plus 1, there's a shorter way to state this. In C or C++ programming languages, we can simply say I plus plus. That is a syntax that means increment 1 or add 1 to I. So it's basically just the short way of the same thing. So basically by saying car plus plus, it's taking the current pointer here and increment it so that it now points to this value. Now you may ask, but how does it know with how much it needs to increment? Because remember, say for argument's sake, at this particular position over there, the start of that node was, argument's sake, at memory position 61. If we would now increment 61, it means add 1 technically, as I've explained to you over here. But in the special case of pointers, C or C++ or Java for that matter will know what the size of a node is. So that is done in the background. You don't have to worry about it. So in this case, it would know that it is actually so many bytes, but not even that. It will actually know that it will have to check where this thing points to at the moment. It points to there, and whatever that address might be, 84 or whatever, then it knows 84 needs to be assigned now to current to effectively make it point to the next value. So again, this plus plus technically means increment with 1, but in the special case of linked lists, if this is a linked list pointer, C or C++ or Java will know that it is a list pointer, and it will simply increment it, in other words, advance it to the next pointer, wherever that is in memory. Again, we don't have to worry about that. C or C++ or Java worries about that, so to speak, and it makes it easy for us just to increment the pointer to the next. So at this very stage over there, it means that pre is now pointing to the current pointer, and the current pointer is pointing to the next one. So we effectively advanced one node. And then we're at the end of the while. We will start again. We will check is current not equal to null. Current will be pointing to something over there, so it's not null. And that's correct, so it's still true. Now, if that thing, that current pointer is pointing to, it points to this thing, it's data, 132. Is that equal to 98? No, it's not. So this thing will, again, advance the pointer. Pre gets the value of current, and current gets incremented. And so we continue. And basically, we technically could have checked for the special case that, you know, if we know this thing is smaller than the smallest value there, we could have ended already. But for now, to make the process just simple and easy, we will eventually get to the end and realize that we're at the end because the current pointer will now be null. It will be pointing to nothing, and that will end the loop. So, and in this particular case, never ever has the if part executed. So in other words, it never got the opportunity to set flag as true. So flag remains false. That's our indicator that target of 98 wasn't found. Let's look at the next instance for case 2. Okay, so case 2 here. Basically, sorry, this is just a bit of an animation showing you how it went to the next one. So now pre was pointing to this pointer, and current was this one there. We checked the data of the current pointer 132 that is not equal to the target. So in other words, the if wouldn't execute, and then we would advance the pointers again. We would check 178 would not be 98, and then advance the pointers again. 201 would not be 98, advance the pointers again. Now you can see current pointer is not pointing to anything, and pre-pointer, the pre-pointer is pointing to 201. And for that reason, it indicates that we did not find this particular value because flag remained false. Okay, let's go into the second case. So the second case here, oh, by the way, this is, sorry, not the, this is still the first case, this is just the output. So basically, we would check after that while, we would do this check. If flag is equal to true, then we would write out to the screen in C++ specifically. This is the syntax to write something out to the screen with the keyword cout, and then say element car data. Now here's the arrow method. Can you remember? That's the alternative method. We could have written the alternative as in the previous slide. I'm going to write it here again, like star or asterisk car dot data. That will yield exactly the same result. Or just car arrow data, which is a minus and what's that now, a larger or less than sign, but it's an arrow, you know, and that format is exactly the same. It means exactly the same as that. So you could have used any one of the two in the C++ language, and just the last word found is written out. So if the flag was true, it would have written out element 98 found. All right, but now it's not the case. Flag is false, so the else part will execute. It will write cout element target. Now target is 98, so element 98 not found. Okay, so sorry, this is now the end of case 1. Now we go to case 2. Right, so this is case 2, as you can see over there. So it means we find it somewhere, and in this case, somewhere in the middle or somewhere in the list, we find the item. So we use exactly the same algorithm again. The algorithm is not changed here. It's exactly the same algorithm. So basically, at first, current points to the first pointer, pre-pointer points to nothing. And then we will see current.data, in other words, 102, is not equal to the target at the moment. So we will advance the pointers. The pointers point like that now. And we see 132, 132 pointer car.data, in other words, what current points to, its data element, is equal to 132 at this stage. And if that is so, set flag to true. That means flag has the value true now, and we return, which means the while ends. This keyword literally lets it jump out of the while, and we would continue whatever is after the while. Right. And that would be the next statement. So now we would check just to make sure if we did find it, because it could be a case that we got to the end and flag was still false. So we check, is flag equal to true? If that is so, in this case it is. Then we're going to write element car data, in other words 132, element 132 found. And that's exactly what was written to the output, element 132 found. The third case, case number 3, we were supposed to find it somewhere in the middle of the list, but it's actually not there. Now here we modify the algorithm a little bit to make it a little bit more efficient for this case. So we will say while current is not equal to null, so this was the condition all along in the previous slides. So while current is not null, in other words, while it is still pointing to something, and this the two ampersands or and signs, the two double ampersand signs means the logical and. So all right, we did logic already before. So how you read this, while current is not equal to null and current data, in other words, that thing that it's pointing to at the moment, is less than or equal to target. All right, so now we're going to make it more efficient to check that it is still valid to continue. And 102 is still less than or equal to 150, which means we can continue to find. If that is the case, now check, is current data, in other words the 102 over there, is that equal to target, which is 150? No, 102 is not, so we advance the pointers. 3 gets the value of current, and current advances 1, like in this case there. Now they've advanced, and we do the same check again. So we check while current is not equal to null, it's definitely not equal to null, and current data, which is 132, is less than or equal to target. It is still less than or equal to target. So yes, we can continue with this while. If current data, which is 132 over there, if that is equal to target, is it? No, it's not. So we jump over and we increment the pointers. So now the pointer is pointing to 178. Alright, so let's do the test. While current is not equal to null, yes, it is still pointing to something so it's not equal to null. And current data, which is 178, is less than or equal to target. No, it's not. It is larger. So in other words, this condition for the while will not be valid anymore, so we will jump out of the while and continue with whatever is after the while, which is basically this if to check that we find it. The flag remained false. Never ever did we change the flag in this case, so the flag is false. In other words, the else part will execute. It will write element target, which is 150, element 150 not found, as you can see in the output there. The last case, case number 4, where this element is actually not found and is even larger than the last element. So again, the algorithm stays the same as before with our more efficient algorithm now. It's moving so ever closer to the final algorithm, which we will see in just a while. Same story again. We will basically see that at this moment current data, which is 102, is not equal to target, because target is 305. So therefore the if won't execute, therefore pre gets the value of current and current gets incremented, and in other words it moved on. Now the same thing happens, and so we will traverse and find every time that the current data is still less than or equal to target, so it will even still advance now, and target, or current rather, will now have the null pointer. So when we get here, while current is not equal to null, and now it is equal to null, so that will make this part false, and with the logic and, doesn't even matter now what goes on there. Basically it means that this while will end, we will jump out of the while, continue after that, and we will find that the flag is still false, which means the else part will execute. It will write element target, which is 305, not found. Just take a note at the syntax over here. The syntax changed slightly here. We didn't say if flag is equal to true. This was the old case, like over there. But this means exactly the same. So why? Because in C or C++, if the value here results in a 0 or false, in other words, if it's not equal to true, if flag is anything else than true, it will not execute. But basically, if true and false are evaluated literally in C or C++, that if a value is 0, it is false. If it's anything else, a positive number or a negative number, it yields a true. So just by actually, because true would be given a 1, All right, so somewhere when we, if we did find that it would be given, true is actually equivalent to the number 1. And then if flag, in other words, if 1, it would mean true. And it would execute. But in this case, flag would still be false, which is actually in the background, a false is a 0. So it will check basically that if it's a 0, if flag is a 0, it means it's false, and therefore the else part actually executes. Okay. Right, so here's the full algorithm, and the full algorithm basically says the name is search linked list. What we will give to this algorithm or this function, remember this is algorithms are implemented as functions here, we will give to this algorithm the list or the head pointer for the list and the target, in other words, what to search for in the list. So the purpose is to search the list using our pre and current pointers. And so the preconditions is that the linked list or head pointer and the target value is given. But what's not given in the textbook as indicated over there is this part, but it's also actually a precondition. In other words, we assume the list is already sorted. Okay. No post conditions, and basically this algorithm return the position of pre and current pointers and the value of flag. In other words, where the flag is going to be either true or false. Okay, so when we start with this algorithm, we know we will have to start with the first node, which we know by now pre will then have the value null and current will have the value of list. Remember, list is just the head pointer pointing to the first element, so therefore that is the same as assigning list to current. In other words, then current will also point to the first element in the node. Now is our algorithm to say while target is less than what current points to dot data, while that is the case, all we can do is we advance the pointer. Okay, so pre gets current and current gets current.link. So we'll show in the next lecture, again, remember y.link. Remember if we had, for example, two nodes like this, I'm just going to make two nodes quickly. There's one node, there's another node, and this is the data part. Let's say, for example, 76 is the data over here, and that is obviously the pointer pointing to the next node. And the content, if this node basically started at memory position number 85, then technically what will be inside here is the value 85 for the pointer. And that will be having some data again, maybe 91, and maybe that's the end of the list, so it's a null pointer over there. And the head pointer basically contains the value. If we assume this thing maybe starts at memory position number 103, then literally that thing has a 103, and that's the head pointer indicating that it points to the first element. Okay, now when we start initially, we say that as we saw over here, this is our pre-pointer. All right, pre-pointer initially has null in it, and current pointer, so this is pre and current pointer here gets the value of list. So list is pointing to the first element there. In other words, it will also get the same value as list, which is 103, which technically means it points to the same element. All right. And now when we advance the pointers over here, first we do pre gets the value of current. In other words, pre was empty, but pre now needs to point to there. All right, and to do that, it needs to get the value of current, which is 103 at this case, at this stage. And now current needs to advance to that one over there. and that means current's address, or the value in current, needs to be the same as what current is currently pointing to. It's this one, its its pointer value, and that has the value of 85. So therefore current now gets the value of 85, which means now it is pointing to the same address or the correct address, which is the next pointer. And this is what we were able to do here by saying what current first pointed to. It pointed to this thing over here, right there, and its link, in other words, current dot link, that's the important part. Its link, in other words, this thing is what we're talking about now, which is the 85. That gets assigned to current, and that's the reason why current has the value of 85 now over there. Okay, now we check after this. So we basically, we're at the end of the while, okay, and we continue with this practice. So we check, is target less than or equal to current data? Okay, so let's say, for example, the target was 80. Right, so target basically had the value of 80. Right, so now we get here, current is now pointing to this value over here, and we see it's 91. Okay, so that means target is less than current or data. All right, it's less than 91. So the while ends. Now we continue here, and we basically see if current or data, in other words, current points now to this thing, current or data is 91. Is that equal to the target? The target is 80, and this is 91, so no, it's not equal to. So for that reason, this part does not execute, it basically gets skipped. The else part gets executed, which basically means flag is false. In other words, it didn't find this value. But current is still pointing there, and pre is still pointing there. So current and pre is returned, as well as the value of flag. So now, after this function, we'll either get a true or a false at where the pointers point to. If we get a false, we know it's not found. If we get a true, then we know whatever current is pointing to, or was pointing to at that stage, that is the value that was found. And we will know at which position, because current is pointing to that. Right, and then we're going to end it here for this lecture. In the next lecture, so all we did in this lecture was really to show you how the pointers get advanced and how the checking gets done to see whether the value is found or not, mainly using this flag value. And it's only a searching exercise we've done. So we've showed you the searching exercises. What we're going to do next, in the next lecture, is now to actually see how we can start adding and deleting nodes and so forth, and that will end this chapter as well. Thank you very much. Enjoy the rest of your day.